So here's a video going over the little old test that I gave you today in class. So the first one and the second one deal with these equations where C is equal to wavelength times frequency and energy is equal to Planck's constant times frequency. So if I go back and look in your notes for the value for C and the value for H, I will use them, but I'm pulling these numbers out of your notes. So 1120 kilohertz, we'll need to change kilohertz into hertz to begin with. So we'd have 1120 kilohertz, and we'd multiply that with kilohertz on the bottom and hertz on the top. And we know that a kilo thing is 1,000 things, so we're looking at 1 kilohertz being 1,000 hertz, or 1,120,000 hertz. 1,120,000 hertz is the same thing as 120,000 reciprocal seconds. Remember, hertz are a cycle per second. You remember the wave, the number of times it goes up and down per unit of time is a cycle. Or up and down is a cycle, and per unit of time is usually seconds, so we measure cycles per second. All right, so now we know that. We're looking for wavelength, so the wavelength equation is this one, so we know that C is equal to wavelength times frequency. We know that C is 3.00 times 10 to the 8th meters per second. We don't know wavelength. We do know that the frequency we just calculated is 1,120,000 reciprocal seconds. The reason I'm using reciprocal seconds here is so that seconds will cancel out when you actually do the math. So the wavelength will equal to 3 times 10 to the 8th, be sure you don't make an algebra mistake here, divided by the 1,120,000. So it turns out to be about 268 meters. 268 meters because up here there are 3 significant figures. Remember, zeros at the end are not significant if there's not a decimal. So we'd have 3 significant figures in our answer. Number 2, we want to find energy. So energy is equal to H times frequency, but we're given wavelength. So there are 2 things you could do. You could use this equation and solve for frequency, because you know wavelength is 136 meters. You know that C is equal to 3.00 times 10 to the 8th meters per second. And we don't know frequency. So you could solve for frequency and take frequency and plug in here. Another thing you could do is realize that C equals lambda nu can be arranged so that nu is equal to C divided by wavelength. So think about that. I didn't like my wavelength sign very well. There you go. So C divided by wavelength. So now you can take this and plug it into this equation. So this equation would become H times C over wavelength. So then you would have 6.63 times 10 to the negative 34th. I'm going to write joule seconds, joule per hertz, but a joule per hertz is a joule per reciprocal second. So a joules per 1 over S, which is equal to a joule second. And C is equal to 3 times 10 to the 8th, that will get 3.00 times 10 to the 8th meters per second. And then you're dividing by the wavelength, which is 136 meters. Now you'll end up with energy in joules, because you see seconds cancel, meters cancel, and you'll end up with just joules for energy. So your final answer would be 6.63, oops, 6.63, oops, because I hit the wrong button on the calculator, negative 34th. I'm multiplying that by 3 times 10 to the 8th. If you're doing this with me, you'll get 1.989 times 10 to the negative 25th, and divide then by 136, and you end up with 1.4 or 1.46 using 3 sig figs. So 1.46 times 10 to the negative 27th. Joules. Okay, so I'm going to double check my math. No, that should be right. So that looks good to me. Okay, 1.46 times 10 to the negative 27th. Now the next one is, oh, I forgot I have these constants down here you can use. Remember I said you have to look in your notes, but here they are. Okay, so this one is your wavelength of a piece of matter. So you remember this equation we derived, and we used it to find the wavelength of a duck, which we found was not significant. But the wavelength of an electron is. So 6.63 times 10 to the negative 34th. That's joule seconds again, joules per hertz, divided by 9.11 times 10 to the negative 31st kilograms. And multiplied then by the velocity of 1.5 times 10 to the 8th. Whoops, it's positive 8, not negative 8. And that was in meters per second. All right, so when you do all the math there, you get 6.63 times 10 to the negative 34th. You're going to divide that by 9.11 times 10 to the negative 31st. And you're going to divide that again by 1.5 times 10 to the 8th. And you get 4.85 times 10 to the negative 12th. So equals 4.85 times 10 to the negative 12th. And the unit's going to be meters. Now I'm going to convince you right here why it's meters. So joule seconds divided by kilogram meters per second. So all I did is write the units from here and the units from here over here. So we'll just show the unit cancellation real quick. A joule, you will remember from physics, was a Newton meter. So we'd have Newton meter seconds over kilogram meters per second. However, a Newton is a kilogram meter per second squared. And then that would be, so that, all that stuff in parentheses is this Newton right here. You still have a meter here and you have a second here. And that would be divided by a kilogram meters per second. So then, this becomes, on top, kilogram meters squared seconds over seconds squared. Now, meters squared, because meters times meters right here is meters squared. When you divide by a fraction, you multiply by the reciprocal. So this would become seconds over kilogram meters. Now do you see what happens with the units? There's a second and a second, which cancels a second squared. There's a kilogram that cancels a kilogram. There's a meter squared that cancels this meter, so you end up with just plain old meters left behind, and that's the wavelength. All right, so there, now we're on the backside, short answer section. You want an orbital diagram showing all the electrons in this atom. So if n equals 2 and L equals 1, that's a 2p sublevel. M equals 0, remember you had negative 1, 0, and 1. We're looking at m equals 0, and that's a clockwise electron, which is going to be the first one in. So you'd have 1s, which has one orbital, like that. Then you'd have 2s, which is going to have one orbital and 2 electrons in it. Then 2p. 2p has 3 orbitals. So that's L equals 1. This is negative 1, that's 0, and that's 1. Since this is the first electron in, the clockwise electron, you'd have an electron going, spinning in this direction and in that direction, and then you'd be finished. So that is the orbital diagram if the last electron in the filling order is 2p, and in the second orbital, it's the first one in the second orbital. All right, the quantum numbers for the highest energy electron, that's the last one for aluminum. So we're looking for aluminum at 1s2, 2s2, 2p6, 3s2, nope, 3s, yeah, 3s2, 3p1. So we're really looking for the quantum numbers that describe that electron. So let's draw the orbitals in just so you can see it. That's negative 1, 0, and 1. So, and there's one electron, so that's the clockwise electron in the first orbital. So what is n? n equals 3. That's the energy level. P is L equals 1. So L, that's 1. M would be -1 because it's the first orbital. And then s would equal +1/2 because it's spinning clockwise. Okay, pictures of an s orbital and a p orbital. I put a little activity online I'd like for you to do. I didn't mention it in class, but it's on the homework link. If you click on that, that'll help you understand this question better. S orbitals look like little spheres. P orbitals look like little dumbbells, like that. And the p orbitals there are 3 of them, so I'll just draw all 3. Although to get credit for this question on the test, you would only need to draw an s and a p. But there are 3 p orbitals. Okay, now all the orbitals you'd expect to contain at least 1 electron in an atom of carbon. So here we go: 1s, 2s, 2p. Okay, and remember if we just drew the orbitals like this, it'd be 1, 2, 3, 4, 5, 6. So you'd expect, what's this orbital look like? It looks like that. What's the 2s orbital look like? It looks a little bigger, a bigger sphere. 2p, one will look like that, and one will look like this, and those are your 4 orbitals. Okay, now the last one, an orbital diagram for an atom of sulfur. So sulfur has 16 electrons, so it'll be 1s2, 2s2, and I'll come back and put the orbitals in just a second. That's 16 electrons. Now if I put the orbitals in, ignore this, there we go. Alright, so here we have, if I do our quantum number values, this is n equals 1, L equals 0, so this orbital m has to equal 0. So I'm going to go 0 down here for the m values. Now, yeah, do that. Okay, down here, this m value would also be 0 because n equals 2, then s sublevel is L equals 0, and if L equals 0, then m has to equal 0. But here, this is L equals 1, so you could have -1, 0, and 1. So it was 0 down here, then -1, 0, and 1. So our 0 orbitals right here. We'll put the electrons in just a moment. Now we've got n equals 3, L equals 0, because that's an s sublevel. So the only value for m, these are our m values down here. M is 0, m is 0 for this one. Our m, man, I'm not handling my pen very well. M equals 0, go right here for that one. And then this one is -1, 0, and 1, so the m equals 0 is that one. All right, so now how many electrons do I have? 16, we said. So putting the electrons in, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So how many electrons have an m value of 0? Well, there's 2 right here, 2 right here, so that's 2, that's 2, this is 2, that's 2, but this is only 1. So our number of electrons with m sub L value of 0, or an m value of 0, is 2, 4, 6, 8, 9. That'd be our electrons in the m equals 0 orbitals. All right, there you have it. The little overview. We'll have time for questions on Tuesday if you have them. Please be sure you come prepared to class with questions.